Hello everybody, welcome to the most crazy, hopefully Yocto live coding session so far. Here I am. You can see a couple of things have changed. First and foremost that I am super cool and fancy green screen by now. So you can see hopefully things going on behind me, which will be probably be mostly the terminal and everything. I don't wear headphones anymore, which means I can gesture around and do funny things and dances maybe. And yeah, that's about it from my posting plans, and we will do just as promised probably the craziest things so far, because we will use a build system that is aimed mostly at creating Linux systems and Linux distributions, and build something that is not a Linux distribution at all. We will be building a binary or an image, probably it's more like a binary, to run in a bare metal fashion, which is kind of like cheating a bit because, as usual, I'm gonna use just qemu. I don't have any suitable microcontroller around, so it is kind of like we will be building a binary that runs on ARM64 hardware, and boot directly into the binary, just like anything you could do on a microcontroller. That's the plan for today. And you will have to put up with a lot of advertising from me today, because it's in 2 weeks that I will be running the Linux Foundation mentorship session on the Yocto project. Somebody can maybe drop a link into the chat. Everybody who has not registered yet, please do so. This will be really, really awesome. I'd like to see everybody of you around. Okay, and I'm just gonna repeat that a couple of times in the next hour or so. And here we go. I will be looking down most of the time by now because my setup has changed a bit. Hopefully everything works today. Just as I said, it is all new and experimental. If there are problems with sound or something, or just tell me in the chat as quick as possible so I can fix stuff up. Again, advertising. This is essentially a test run for the mentorship. So, and where are we? Hopefully, MNT heap session 20. It's actually kind of an anniversary. It's the 20th live coding session, which is crazy if you think about it. Okay, hi Macro. So I have actually prepared a Pocky checkout, which will just get rid of the build. And yeah, what does it take to build something for bare metal? Obviously, a properly prepared session, which I kind of like failed at again. There will be lots of failures, as usual. There are always failures during my sessions. And okay, this is the first, literally the first line I type, and I have to babble myself out of something, as usual. What can I say? We will also be looking at the code a little bit, but only after we have actually built it, because there's something a little bit special to it, and I would like to like show that and discuss that. Other things, yeah, maybe you have noticed that there's a lot of cool stuff coming up in the next Yocto, and therefore also open embedded release. There's been mostly a technical change for appending syntax or the override syntax, which means that layer maintainers might have to change and fix their layers. But just recently, last week, Rust support hit mainline for us, which means that from the upcoming release on, Rust is kind of like a prime language that is supported in the Yocto project. I've seen the patches coming in to fix the last like rough edges since Monday, and that's really annoying when you just want to start out and you like messed it up. Okay, but then let's do it some in another way. We can always just create a new build directory. Build 20. Let's call it build 20 because anniversary 20 session. Okay, here we go. Where do we get our bare metal recipe from? Let's give it a try. Bitbake. Hello world. Bare metal. No, don't let's not do that first. Let's first fix. As promised, we're going to build for qemu arm. Is the terminal readable and everything? This is also a completely new setup. I'm streaming from an SSH session directly into a Google Cloud instance, and hopefully this works as well. So this is not exactly a session for hardcore beginners, because I'm pointing the download directory and the state cache to something prepared. Otherwise, the session would have taken until tomorrow probably, which is not what I actually planned. So heap caches, and yes, except red on black. Okay. Let's see if we can fix that in some way. But I agree, this is unfortunate. So, as you all know, downloads and state are meant to be preserved across builds to speed them up, and this is exactly what we're going to do here. So, bitbake, hello world, bare metal. Typo me. While that parses, let's see FARP designs. Right? Is that better? Just avoid using strings. Better to read now. I think there might be even something more crazy. Designs, customer. I think that's better, right? Font. Oh, okay. I guess that's the best. We can get in the like next 10 seconds. Okay. I'm babbling all the time, as usual. You know me. Because this is not a sales webinar. We are like doing stuff, and as most developers know, when you're doing stuff, like 80% of that doing are actually waiting. Nothing provides hello world bare metal. Surprise. Actually not. So, where could we get that from? Where's my mouse? Here's my mouse. Okay, let's look at Pocky. Because I am somewhat prepared, of course. And in Pocky, there's a layer that provides a couple of examples, which is meta skeleton and surprise recipes bare metal. And if you look there, there's a directory bare metal examples. And okay, I even swapped it around, but there's a recipe that's called bare metal hello world. So in order to actually use that layer, bit bake layers, add layer, Pocky, meta, skeleton. And as promised, I messed up again. Bare metal, hello world. Give it another try. Maybe if everything works out and I'm super happy after the session, I will post a picture of what this all looks like in real life on Twitter later and on Instagram. And then you will understand why I'm drinking so much. It's because I'm sitting in the roof floor of a house in the bright sunlight, and I had to basically like carry everything up in order to make a proper streaming setup, which makes me super pretty for you, but it was quite an effort. Okay. What's going on here? Nothing progress. Bare Metal Hello World was skipped because incompatible with Arch. That was not what I hoped for. Not incompatible host. I actually hoped for another message, but it probably is just like in disguise, because I'm gonna drop the link into the chat already. If we would look into the recipe, why would we can look into the recipe? Crazy me. Meta skeleton recipes, bare metal, hello world. Then you can see that this link is actually where stuff is going on. I'm gonna drop you that link into the chat so you can have a peek for yourself already. But let's check what's going on there. qemu arm. This should hopefully like work. qemu arm 46. And actually I would have expected to like it complain about the libc, because if you look at the sources, then there's a readme, which is good, and it states this is what you have to do. Set machine, I did that. Set tc libc. I would have hoped that the error message would be like clearer, but we will see if that actually was the problem. Okay, it's really way more readable. qemu arm looks good. Okay, and no, we always add the tc libc is bare metal. Let's see if that works out now. And then I think I can explain the error that just happened. But yeah. Let's just see if it parses well enough. Okay, we changed something in local.conf, which means that actually everything has to be reparsed because a config file is injected everywhere. Feel free to sing along with me. Recipe data is local, configuration data is global. This is a session that has way too much babbling of me and way too little live coding. Seriously. I could do some more advertisement. If you want to see a better prepared session, join me for the mentorship. Okay, here it comes. This obviously did the trick. And what was the problem? The problem is if you want to build for bare metal, it's one of the main things that you actually have to care about is the tool chain. And in the Linux world, and especially in the GCC world, the tool chain is defined by the triplet of target machine, distro, compiler, which in our case is ARH64, Pocky, which is our distribution, and GNU Yavi, whatever. Okay, so the message in disguise, it is a machine not compatible, actually meant the toolchain is not compatible. Because when you're building for bare metal, you can't or cannot easily use a toolchain that goes for the GC-libc. Why? The GC-libc actually relies on a bigger, let's call it operating system to be there, like providing threads and everything. And if you explicitly tell BitBake or the Yocto build, okay, here's a setup that just that I want to run on a bare metal machine, then you don't need all that toolchain or the GC-libc stuff, but you want a toolchain that can do the trick to run or to build something that runs on bare metal without a lot of the hoops that you could jump through if you want to use GC-libc. And therefore, you explicitly have to say, okay, GC-libc, which is the variable in which you set the libc you want to use, is bare metal. And then BitBake and or open embedded / Yocto actually takes care of evaluating the toolchain in a form that is suitable to build something for bare metal. Okay, hopefully that worked out now. And let's see what actually has happened. Run qemu. Slurp. Slurp is just like, I don't want to use ton-tap networking. And what happens? It falls over. I would have expected some output, which is not there. Which is really sad. Okay. Run qemu? Ah, no graphic. Hooray! We did it. We just built a bare metal application running on ARM64 and saying hello open embedded on ARM64. 20 minutes in. Achievement unlocked. Time for a beer. Marco asks, what is the purpose of building bare metal on Yocto Project? Yeah, it depends on your use case, obviously, but there are a lot of companies who do build for micro. Okay, there's two use cases. Either you develop something directly for a microcontroller or a bare metal platform, then your setup is often quite convoluted. You have to make sure that there's the compiler installed, that all the bits and pieces are on the machine, and then your hand-carved makefile will make use of it and hopefully produce something that you can use. This is the first use case. If you put all that into into a Yocto recipe, then Yocto takes care of this for you. You say, I want a toolchain, and then you can use it and build it. So first problem is toolchain setup problem mitigation. Second use case is, and this goes back to to one of the earlier sessions where we did build in build. A lot of systems are increasingly complex these days, and they have multiple processors, and not all of them are running Linux. So imagine you have a system where there is one big Linux core and like 3 microcontrollers around them. Then you can either like pull the firmware blobs that go into there from somewhere by magic and relying on other stuff, or you can do a multi-config build, like sub multi-config 1 is a bare metal build for microcontroller 1. Sub multi-config build 2 is a bare metal build for microcontroller 2. Same for 3, and then there's the master build that pulls in the bare metal firmware blobs and then uses it for whatever the application needs. So these are the 2 use cases that I actually have like gathered and understood. Okay, build has succeeded. It has shown us something. Now let's use the rest of the session to dive down into the nitty-gritty details that are like all working together to make this happen. And drinking beer. And of course, advertisement, 2 weeks, Linux Foundation mentorship. So, where is my cursor? Now that we're not in in the graphic mode again, not anymore. Okay, that's how it looks. Control C doesn't work, so we have to actually like kill qemu the hard way. Grab qemu, kill, here it is, and we're not gonna need it anymore. Did I get it? Okay, I got it. Because first thing we're gonna do is we're gonna get the sources, DevTool, modify, bare metal, hello world. So you can see and understand that it is really just like 30 lines of code all in all. But other things are there. I'm not just like randomly jumping back and forth to some other window, because DevTool modify really gets the exact sources that we just used. So this is basically the proof that I'm not cheating. I do cheat, but then I wouldn't tell you. As usual. You know that. I need a bigger build host next time. Okay, where are the sources? Build workspace sources. Okay, here we go. What? Workspace sources bare metal hello world. Now you can see there's 5 C files for the different architectures that are supported. We're going to look at AArch64, obviously. And that's it. That's the whole program that we just ran. It's like, let me see. Where's my mouse? Here's my mouse. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 lines of code, including one definition and 3 closing brackets, which is kind of like awesome. Essentially, we put out a string in 5 lines. Why did I talk about 30 lines? Because there's something more to it. But let's just have a small look what actually has happened here. This is the entry function, which uses print UART0 and a string. Print UART0 is defined right above. It takes a string. And what does this do? It just iterates over the string and puts each character one after the other into a hard-coded address in the memory space. Okay, for those of you coming from the Linux world, this is like super crazy. For those of you having done bare metal, this is like piece of cake, right? You always do tinker with registers somewhere in your memory map all the time, because this is actually like you write drivers there. So what is basically happening there? The guy who wrote that piece of code just knew from looking at the documentation and the datasheets that if you write something into this particular register, it will be piped out through a serial port, and then the register can be rewritten, and then it will be put out again. So this is essentially a super simple serial port driver. This print UART. It takes a string and it puts everything onto the serial port. And we can print whatever we want. If we are super quick, then we might actually recompile it with some other message, just to be super sure I'm not cheating you. Okay, but these are like 10 lines and I talked about 30 lines. Why did I do that? Because I looked at the sources earlier. And maybe you have spotted the comment C entry as called from startup S. And here we go. We got to look at startup S again for each architecture. And here we kind of like go down into the dirty trenches of bare metal. It's not much, but about every form of bare metal programming that I personally have ever seen so far requires at least a little amount of assembly to get started. This might include setting up stack and heap and defining where to jump and everything. So this is a super simple program. It doesn't use a heap, no nothing. So it's really the absolutely bare minimum that you can actually use. And it looks like this. It defines a symbol called _start. It loads the stack top into a register, moves the register into a stack pointer, and branches to that function. And after that, it loops forever. B dot is while true in assembly as far as I know. So that's another 5 lines. If you look at real world code, things become more complicated because you usually want some form of heap, which is more involved at times. Okay, and you have noticed that that this also just exports a symbol. This does not say okay, this is what I'm gonna do to the CPU, because there's the last bit missing, which is the linker file. And I personally hate linker files. This is really like a feud between the linker and me, and I keep on losing. So whenever I have a linker file that just works, I use it. Okay? But for the sake of explaining it, this is the core bit that makes a bare metal application work, because it defines where in the memory map the code goes. And here, if we look at it, qemu obviously puts the RAM at 40 million. qemu, when given a kernel, adds 1000 hex, which is very good that it's noted there. I would have no idea why it does that, or 10k hex. And then there we put this startup code, and this is essentially the first assembly instruction in startup S ends up at the very memory address that qemu jumps to. And that's the core trick. There That's whatever makes everything work. The rest is just like pulling in stuff that you want. You want the rest of the code in forms of the C output. You want static data, whatever comes with it, and you want a stack usually, because without a stack you wouldn't even have a pointer that can iterate over the string to use. So these are the three things that you usually need in order to make a working bare metal application. You need some form of entry function. You can call it C entry, you can call it main. It really doesn't matter. You need some form of startup assembly. This has substantially reduced in the last like 10 years. When I was starting bare metal coding, almost 20 years ago, the assembly that you needed to just go into a C function was like 1,000 lines. And since ARM v7, they changed it drastically, and usually like a couple of 10 lines are okay. This is really the super bare metal down. And the linker script is what ties everything together. We have a question from Dr. Dougal. Yep, exact. You're completely right. ARM actually starts at the interrupt table at 0. This is a qemu specialty, that when you pass the parameter kernel whatever to qemu, then it actually means like this is where you jump off. Great question, really. Again, advertisement for interaction. Whatever you want to ask, remark, insult, praise, just drop it into the chat. I try to keep an eye on it. You can ask me about everything. I just don't promise that I have an answer to all the questions. If I don't know, I will tell you that I don't know. If I happen to know where to look, I will tell you. And if the question is too far-fetched, I will tell you, let's talk about it later. That's what can happen. Oh, and don't ask if you can marry me, because I'm already taken. So, what's left for us to do? We looked at the source. We looked at the build. We looked at the configuration. We looked at actually running it. And that's now the last thing we want to do is we gotta look at the recipe, because you might have guessed that a bare metal recipe can look a little bit different. So, what's going on there? Summary is not that much of an enlightenment. Okay. Do I have a cursor there? No, I don't have a cursor. That's like, nah. Okay, but here are a couple of things that are not as usual when you're doing a bare metal build. When you're building bare metal, you're not doing a file system. You have to get that into your head. Usually, when you're executing an open embedded or a Yocto build, you want some form of root file system to fall out in the end, maybe accompanied by a binary for the kernel or for the bootloader or whatever. And sometimes not. Sometimes you want that to actually like be in the file system. When you're doing bare metal, you don't want a file system. You want that one binary blob that you can just like kick off directly. Therefore, in Yocto terms, the binary is the image. And that's what we're doing here. Where is my mouse cursor? This is really annoying about the new setup. I think from the lack of complaints, I think that my sound is understandable and nice and clear, and I'm looking good, a bit pale because of the lighting, and it is well readable. Is that I think that holds true. Fair enough. And yeah, okay, let's go back to this. And in order to tell BitBake that this recipe, which produces a binary, is actually to be treated like an image, you have to set a couple of variables like this. And if we go down further, then we notice that one magic line. Inherit bare metal image. This is the one piece that makes it happen from the Yocto side of things. This is my microphone here. This is a class that is essentially doing all the tricks to make a binary treatable just like you would expect from an image. And this class is also responsible for the I don't know. I need more beer. This class is also responsible for the check that I wanted to show you right in the beginning. So yes, I expected it to fall over because that class checks if you actually have set tclibc to either bare metal or to newlib. Newlib is a form of libc that is suited for use in bare metal applications. I haven't dug down into the details on where to use bare metal and where to use newlib. I think if you actually have a use case for that, then you are capable of doing that yourselves. And so if you ever want to do bare metal, you actually have to use this class. We might be able to look into it. We're pretty quick. As you can see, building a bare metal without all the babbling, with what comes with Yocto actually takes you like 10 minutes. We've just used up 37 by now because I talk so much. And you might know this from other recipes, especially from kernel recipes. They are only allowed for specific machines, which is completely legit and makes even more sense in a bare metal context because whatever you do, it probably works only on that one machine. Best example is the UART register. It will be completely different, even as if you would be talking about a real microcontroller. The microcontroller peripheral address in memory would probably be even different for something of the same manufacturer with the same processor core in the same family, just a different derivative with other peripherals. It just like it's bonkers all the way. So nailing the machine down is essential if you're doing bare metal. Okay, this is essentially just like making it verbose. We're setting a qemu arch, which is only relevant so we can use run qemu. In case you haven't noticed, run qemu is something that is actually not that common if you're doing bare metal. You usually go right to the hardware. And Yocto is doing quite a lot of magic behind the scenes to make qemu work for all the use cases that are in the core repository. And this is part of that. And in the end, yeah, well, these are the images that we created. And this is how they're packaged. So I'd say we actually are done with the content that I wanted to do. So time for another advertisement. Follow me on Twitter, follow me on Twitch, follow me on Instagram, follow me on LinkedIn. microphone. Follow me wherever you want, just not in real life, because then I get paranoid. And don't forget about the mentorship session. Now let's do the stuff that is like optional. Optional is we can rebuild from source with a different string. And okay, that's let's just do that. That's the first thing. We have source now, and we're gonna change workspace, sources, bare metal, hello world, bare metal, arch, C, and hello live coding peeps. Line feed looks good. Let's go for it. That was fast. Let's run it. Hello live coding peeps. So, no cheating. I actually used that code. Where is it? Where is it? Where is it? No, it's 6. Okay. I just had something else on my mind that I wanted to show you. But now I can't remember it. Which is kind of sad. Do we have any questions, be they related or unrelated, for the time being? Just throw me whatever you have on your mind, so I can like think about what I wanted to tell you. Because I think we have covered all the important bits and pieces. But I really don't remember what I wanted to tell you. Because if there are no additional questions, then I will just like say, okay, everybody's super happy, everybody will be running off and doing bare metal builds right now, and call it a day. I really don't remember. I said one can leverage multi-config to equip the Linux system with a firmware for a coprocessor. Exactly, that's what I said. So, what is the question then? Someone that didn't, yeah, exactly. So, this is highly hardware dependent. Depending on how the coprocessor is connected, there are a number of ways that could be used for this. If it's a combined system like the Freescale Vibrates, where there is there is a coprocessor right on the same address data bus, just as the main CPU is, then you can usually go for RP message or the remote proc infrastructure, which is a part of the Linux kernel. Then you don't even have to write a lot of magic, because there's examples in the Linux kernel code on how to use such a coprocessor, how to put firmware there and run it. If it's custom hardware where the coprocessor is connected over some other wire protocol, then it's actually a two-part solution, because you would have some form of user space application that can talk to the coprocessor, which is maybe connected over SPI. So depending On the specific coprocessor, then you might be able to load the firmware just into RAM of the coprocessor. If you pull it out of reset with some magic on its I/O lines or whatever, or the coprocessor has own flash and is running its own super simple bootloader that can be updated from the Linux application. Then you would obviously have to write some form of user space that can like push it there. In today's world, there is what's it called? Not DMX. It's called. There is some tool that is used very often for flashing microcontrollers. I don't remember it from the top of my head. And so if you have that situation that a Linux processor would need to flash a coprocessor there, you would need an application DFU, exactly DFU. That's it. So you would, if you do the hardware, you would in the optimal case, you would make sure that the coprocessor is connected in a way that DFU can directly trigger, and then you would just like write a small script that upon boot of the Linux processor flashes the coprocessor over DFU. It finds the firmware in lib where you just like dropped the bare metal firmware, and that's it essentially. So it really boils down to the hardware. I can tell you that it is really doable. We're doing it at my company, my day job. We do really have the situation where we flash out binary firmware to a microcontroller from the Linux like main CPU. But again, it's highly application and especially highly hardware specific. Other questions? I can't. What I haven't done so far yet, I haven't combed my beard. It's time to comb my beard. You should also enjoy the sound. It's awesome, and it feels great. Well, then, as there are no more questions, again, final advertisement. Don't forget about the Linux Foundation mentorship session on September 15th. It's about the same time. It's 3:30 Berlin CST time, and we'll be talking about a Yocto quick start on RISC-V. Essentially, now that you are listening, you're the first to get the announcement. From the mentorship session on, I will try to highlight a lot of the cool stuff that RISC-V can do and how to leverage from the Yocto Project side. So this is probably has been the last session that was using ARM. Okay, and then again, follow me on Twitter, Twitch. Send me an email. Send me a postcard. You can't see me anymore, but you can hear me. I'll have the rest of my beer, and thanks for having me. Bye and take care till the next time.